Lightning strikes are a menace not only to human lives, but also to the IT equipment and devices that are universally used in our daily lives. Damage to such equipment and devices is a critical issue in contemporary society. Effective lightning countermeasures are required in all fields, not only homes, offices, and plants, but also the so-called lifeline, that is electricity, water supply, and gas, traffic, finance, and medical arenas. Under an innovative concept of preventing lightning strikes, Hitachi Plant Technologies proposes the integrated lightning protection countermeasures to protect these indispensable facilities from lightning damage, which is sometimes difficult to prevent with only conventional lightning rods. How is lightning formed? Let me first explain the basic mechanism. When strong direct sunlight beats down on the Earth, updrafts are formed and develop into a cumulonimbus cloud. In a cumulonimbus cloud, electric charges are generated due to the collision of small ice particles and hail pellets influenced by cool airflows in midair. The electric charges are distributed with positive and negative charges roughly separated in portions of the thundercloud. Negative charges concentrate at the bottom of a cloud, or the cloud base, whereas positive charges concentrate on the Earth. Such an electric charge distribution generates a large electrostatic field between the thundercloud and the Earth. As the electrostatic field develops, an advanced discharge extends in incremental steps from the cloud base to the Earth. This phenomenon is called the stepped leader, through which the voltage level reaches approximately 100 million volts. As a stepped leader comes closer to the Earth, the ground-based field ascends to counter the approaching leader, thereby generating rising streamers that extend from the ground. A stepped leader that has developed into the final stage is connected with the nearest rising streamer among the many that were generated on the Earth. At this moment, a lightning strike occurs. This map shows a distribution of the days annually on which lightning occurred, issued by the Japan Meteorological Agency. The larger the circle, the more numerous the days when lightning occurred. The largest circle indicates that lightning occurred for more than 35 days annually, according to this chart. At a glance, it appears that lightning was mostly concentrated in the Hokuriku, Kyushu, and northern Kanto regions. Japan has two types of lightning. Summer-type lightning usually has a distance of 2 to 5 kilometers between the ground surface and the thundercloud. The scope of the lightning strike is narrower and the energy not as strong as with winter-type lightning. Winter-type lightning has a low cloud base of only several hundred meters. Such lightning strikes often tend to discharge higher levels of energy at one time than summer-type lightning. This chart also indicates the ratio of the occurrence of lightning by season via color coding in the circle. Analyzing the circle graph data by color shows that winter-type lightning often occurs in regions along the Japan seacoast. Conversely, summer-type lightning is generated mainly in mountainous areas of the Kyushu region. It is also necessary to understand the characteristics of lightning in each region to take effective measures to prevent lightning strikes. There are two types of effects of lightning strikes. One is a direct strike whereby lightning directly hits an object. The other is an indirect lightning strike whereby lightning strikes near an object. When a lightning rod receives a direct strike, a large current of several tens of thousand amperes passes through the lead-in conductor and the earth electrode. This passage of a large current produces a magnetic field. Abnormal amounts of current might pass through power and communications lines due to electromagnetic induction if these lines are within the magnetic field. When a large current reaches the earth electrode, the voltage at the grounding point rises considerably. Such abnormal levels of current and/or voltage are called a lightning surge, which is a key factor in damage to electronic equipment and devices. Next, let's look at the effects of an indirect lightning strike. When a nearby place is struck by lightning, the induced charges surrounding the strike spot are neutralized, with the positive charges simultaneously moving to the strike spot. This earth current produces the lightning surge, and the lightning surge penetrates signal cables such as the data and phone lines that are buried underground. Consequently, physical damage could be caused to PCs and/or telephone sets, or a malfunction of any electrical equipment could take place within a radius of approximately 2 kilometers from the center of the lightning strike. Sometimes an indirect lightning strike penetrates overhead cables. If a thundercloud appears, positive charges are induced inside overhead cables such as power and communications lines. Although such positive charges are bound within the overhead cables before a lightning strike occurs, they will be no longer bound after a lightning strike and will move simultaneously, thereby producing a lightning surge. The lightning surge penetrates inside buildings and could damage electronic devices. It is possible that such lightning damage could be avoided if the lightning strikes themselves could be prevented. So, let me introduce a new lightning prevention system. The Dissipation Array System, DAS, differs from conventional lightning rods and is aimed at deterring lightning strikes. The DAS was developed by Lightning Eliminators and Consultants Incorporated, LEC, in the United States. Since 1971, it has been globally delivered to more than 4,000 facilities, of which 200 are mainly public institutions in Japan. The DAS system configuration is simple. The core components of a DAS are an ionizer to dissipate electric charges, a grounding system composed of an earth electrode called chemrod and earth current collecting wires to collect charges on the ground, and an earth conductor to connect them electrically. None of these DAS components requires electricity or any other power. Of typical ionizers, stainless dissipation wires, which are most often used, are installed at the outer circumference of the top location of buildings. An umbrella-type ionizer with an arm on which dissipation wires are spirally wound is installed on the top of high-rise structures such as telecommunications steel towers. A ball ionizer with needles pointing outward is installed on the upper raised portion of buildings and/or the ring of telecommunications steel towers to locally mitigate the electrical field. Chemrod, used as an earth electrode, is a chemically activated type hollow copper pipe of approximately 7 centimeters in diameter and 1.8 meters in length. An inorganic salt that fills the inside of the pipe dissolves and oozes out through the pores of the pipe surface, and low resistivity is maintained throughout the year due to the chemically synergistic effect of the oozing salt with the surrounding gas. And the maintenance of the DAS is hassle-free. Next, I would like to address how the facilities are protected against lightning using these constituent devices. The grounding system that has collected charges on the ground surface and the ionizer will soon have the same potential via the earth conductor. As the electric field intensifies, discharges occur at the tip of the ionizer needles. Rising streamers are generated from the surrounding structures and/or high trees which are not covered by the DAS protection. The ionizer continues to discharge electricity and delays the development of rising streamers that are generated from the protected facilities. The stepped leaders extending from the thundercloud repeatedly develop toward the earth and end up as a lightning strike by connecting with a rising streamer generated from any facility that is not covered by the DAS protection. As explained above, the DAS prevents lightning strikes by retarding the development of rising streamers on the periphery of the protected facilities for the protection range shown in the chart above. Meanwhile, the lightning surge caused by an indirect lightning strike penetrates metal wires, such as cables and wires, and could damage electronic equipment and communications devices. A surge protective device, SPD, is used for the DAS to prevent the penetration of a lightning surge into equipment and devices. In the chart above, such SPDs for power supply are installed at the service entrance of buildings and the primary side of the protected equipment or devices to protect the whole power line. The SPD for signals is installed to protect fire alarm panels, security cameras, and remote control devices. The equipment and/or devices to be protected are clearly specified to select the type of appropriate SPD and determine the position for installation by studying possible surge penetration paths from power supplies and/or grounding systems. I have explained the lightning protection mechanism by the DAS. Now let me introduce some data that show the proven success of the lightning protection effect of the DAS. The DAS was installed in the Kyushu Hita plant of Sapporo Breweries Limited, located in Hita City of Oita Prefecture. This chart of lightning strike analysis data plots the spots of lightning strikes in a time series that occurred in 1 hour from 4:30 p.m. to 5:30 p.m. on a day when large-scale thunderclouds appeared above the plant. Despite the many lightning strikes that occurred in the vicinity, no lightning was recorded within a 1.3-kilometer radius of the DAS installation point, which is at the center of the chart. In fact, the plant had been seriously damaged by the shutdown of production lines due to lightning strikes almost every year before the DAS was installed. Since its implementation in 2001, however, there has been no lightning damage reported. The DAS has been delivered to more than 200 institutions in Japan. About half of these deliveries have been for facilities that require high reliability, such as those of the Ministry of Land, Infrastructure, Transport and Tourism. Finally, let me introduce several types of installation sites. Telecommunications steel towers at radio relay stations in the telecommunications field. Observation facilities such as astronomical observatories, and railway control offices and rail yards. The DAS has been installed at dam control posts and a wide variety of related facilities. It has also been installed at plants, hospitals, and intelligent buildings. Overseas, the DAS has been installed at airports, power stations, and even amusement parks. Lightning damage is harmful to our essential data, assets, and lifelines. The DAS is a new generation lightning protection system to prevent not only direct strikes, but also the occurrence of lightning surges, which are sometimes difficult to prevent with conventional lightning rods. Please take this opportunity to study the implementation of DAS.